In physics and engineering, energy is defined as the capability to do work. Now that work can take a variety of different forms. It can be electrical work, mechanical work, and the energy can take various different forms as well. We'll study some of these: kinetic, there's radiant energy, potential energy, chemical energy, and others. And so the law of conservation of energy, which is a basis for the first law of thermodynamics, we'll look at thermodynamics a little bit more deeper into the year, states that energy is neither created nor destroyed. So it can change forms, but it's not going to be created or destroyed. Now for engineers, depending on what we're working on, it's important to keep track of energy changes within a system. So if we think of the universe as being kind of the general surroundings, we might have a localized system that we're concentrating on, and we want to see how energy is exchanged between the boundaries of that system and the surroundings and the universe around it. So we can have energy exchange between the system and its surroundings and the universe. So the energy changes within the universe are going to be zero, but the energy changes within the system could be either positive or negative depending on which direction that flow is taking place. Now, mechanical work is defined based off of Newton's second law, so F equals ma. And so we define mechanical work as being a force times the distance along which that force is being applied. And so the force and the distance are parallel to each other. So whatever the orientation of the force is, the distance is going to be measured parallel to that force application. Now the units for work and then energy as a result in SI units are then going to be newtons times meters, so the Newton meter or joules. And then in English units, we've got pound force is our measure for force, and so then the distance is going to be in feet, so we've got foot pound force. So it's always written in that foot pound force order rather than pound force times feet, just for reference. So if we look at the example here, what is the work required to lift a book with a mass of 1 kilogram to a height of 1 meter above its initial position? We want to make that measurement in joules and then convert that to our foot-pound force using the conversion factor that's given to us. So work is force times distance. So I've got my work is going to be, the force is just going to be the weight of the book. So that's going to be m times g, and then I'm going to multiply that times the distance. So my mass for the book is 1.0 kilograms. My acceleration is going to be the acceleration due to gravity, 9.81 meters per second squared. And then we're just raising it by 1 meter. So we can see our units are going to work out to Newton meters or joules. I've got two significant figures, so I'm just going to end up with 9.8 joules as my answer. In foot-pound force, we're going to do the same thing. So our mass, we're going to use the conversion here. So our mass is going to be 2.2 pound mass times acceleration due to gravity in English units is 32.2 feet per second squared. But because the mass is in pound mass, we do need to use g sub c. So we're going to have that 32.2 pound mass feet over pound force second squared. Don't want to overlook that. And then of course we're going to multiply that times the distance. So we're moving at a height of 1 meter. So our conversion from meters to feet, the equivalent of 1 meter is 3.28 feet. So just to do a little units check to confirm that we're going to end up with what we want. So first of all, our 32.2's cancel each other out. Now let's work on the units. Pound masses go, feet per second squareds go. The only units left over here are pound force in the bottom of the bottom, so that's going to move to the numerator. So we indeed are going to end up with pound force and feet up top. So we're just left to multiply 2.2 times 3.28 and then round to two significant figures. So we're going to end up with an answer of 7.2, and then again remember it's foot pound force are the units for work in engineering English. Now as we mentioned, energy can take a variety of different forms and it can change through a series of processes that are applied to an object. So, for example, if we take a book and we lift it off of the table, it was at rest, but now we lift it from the table, so we've given it some potential energy. We've done work on the book, so we've increased its potential energy. Then we drop it, and that energy converts from potential to kinetic energy. Then we take that kinetic energy, it then hits the ground, and so now that energy is dissipated because it doesn't just disappear. We don't all have the potential energy anymore, we don't have the kinetic energy, but between the increased vibrations of the molecules inside of it in the form of heat, or the vibrations in the ground, or the sound wave that's generated from the book hitting the floor, we have a whole variety of different energy forms that end up in our process. And so here, just to take a look, to give a sense of what a measurement of energy in joules means. So from the kinetic energy of an apple falling a meter of being 1 joule, all the way to Hiroshima atomic bomb of 10 to the third joules, gigantic number, and then just impossible to wrap our minds around is what it looks like when you have a supernova explosion out in space. But you can see like there's some perhaps surprising piece of information here. So a small meal is on the order of 1,000,000 joules, whereas a speeding bullet is only carrying the energy of about 10,000 joules. So just a point of reference to give us a sense as to what the energy or potential energy contained in various objects looks like. So besides work or energy content, we're also interested in how fast that work is done. And so that is a measure called power. And so that is taking a look at the time rate of the change of energy. So in SI units, we use watts, which is joules, or Newton meters per second. And then in engineering English, we've got a couple different options. We've got horsepower, which is the equivalent of 550 foot-pound force divided by seconds. So in both cases, we can see that it is a energy per unit of time measurement.